Alrighty, folks. So you guys, at the beginning here, I passed back all the papers that I had of you guys. Let's wait maybe until next class or so to ask questions about the test, give you a chance to look through, read what you did, see some of my comments. Be happy to take questions, but let's just wait on that till next time maybe. Today, well, last time actually, let's start with that. I had given you guys the derivatives practice sheet to kind of work on while I was gone, right? And it was okay. Again, the difficulty knob slowly dialed on that. By the end, it was pretty brutal. The things at the end, more difficult than anything you would see either on a test or a quiz for me, an AP exam. It's purely if you can handle this, you can handle anything kind of situation. So I threw the whole deck of cards at you as a, ideally it's a confidence builder that if I can hang on to everything through this and I can see my way through the order in which I have to attack this thing, when you have only two things going on, it's gonna feel like a piece of cake. Did you guys have any questions from that handout? I have my answers I posted in here on the onto the OneNote, and I didn't get a chance to proofread these, but I hope, fingers crossed, that everything was pretty okay, and they're relatively complete solutions, so if you didn't see those, they're in there, and if you want to look things over and see what I did or how I did things, oh, that was very sneaky, Mr. Kulik. You can do that kind of at your leisure, but if there's anything you guys want to ask about here before we start, or pick up where we left off, just providing a moment for that. Okay then, that's fine. We'll pick up where we left off in 3.5. So we were talking about implicit differentiation, right? And I think we were left on this example here. So it says to find y prime if sine of x plus y is equal to y squared cosine x. So again, we'll start by just taking the derivative of both sides. And again, the ddx symbol is the name of the derivative operation. It's like a times sign or square root symbol. It doesn't have a variable attached to it. It's just saying you're taking the derivative with respect to x. So x is the variable that you're differentiating. So if I look at the first piece, I'm taking the derivative of sine x plus y. That's a chain rule. The outer function is sine, so the derivative of sine is cosine of the inner, and then times the derivative of the inner. We'll get to that in a moment. And the second piece then is y squared times cosine x. To differentiate that, I need a product rule. Very good. So again, that's going to be y squared times the derivative of cosine x plus cosine x times the derivative of y squared. I think I'm going to do one of those. So far, so good. Okay. Let's handle this next layer of derivatives. So the derivative of x plus y, we can just take one at a time. The derivative of x is 1. The derivative of y is 1. And because it's with respect to x, I now get a dy dx along with it. Or you could write it as y prime. I like writing dy dx because I lose the prime sometimes. I don't lose the dy dx, you're not going to lose that. And now you don't have to write the 1 there. I'm going to write the 1 because these are notes. If you're going back and looking at it, I want it to be clear what I did there.
So, okay.
Yes, go ahead.
Taking the derivative of y, I'm not like understanding why you're adding on the dy dx after it. Like, because there's like the x, you don't have to add it, but since there's y, you do.
Yes, so if I was doing, if instead of doing dx, if I was doing dy, I would have gotten a dx dy when I differentiated x, and I've gotten just a regular 1 when I differentiated the y. So like, so the variable of differentiation gets no differential piece with it when you do the derivative. Any variable other than the variable of differentiation gets a differential piece with it. Does that feel okay? And we've really been doing that the whole time, right? When I had like y equals x, I wrote that as like dy dx equals 1, right? So I've been doing that the whole time. We just haven't like made it a thing. Oh no.
That's a ddy
Of x plus y.
X plus y. Okay.
Yeah. Yeah, sorry, my penmanship is sometimes less than spectacular. It's a cross I'm going to live with. All right, everybody's okay? Still doing so far so good? Okay, continuing on to the next chunk. The derivative of cosine x is negative sine x. The derivative of y squared is 2y dy dx. Yeah.
So just because if the dx thing doesn't have the variable and the variable you're trying to take the derivative of, you have to add it.
Yes. Yes. Yeah. The worst would be if you had like sine x plus y equals y squared cosine x, and you have to do like ddt. And now it doesn't match any of the variables in it, so everything gets like a differential. It's like, oh my gosh, what a mess. Just wait till 3.9, and that's what happens there. I know, it's like it all builds on each other, right? All right. So what we're looking for is the y prime or the dy dx, right? So I got to get those onto the same side. So now it's just algebra time. The calculus is now finished, right? All the derivatives are done. I just have some algebra to get the dy dx by itself. It's in 2 different locations. So I'm going to start by uncoupling it from multiplication, specifically here. So I'm just going to distribute the cosine xy through, or cosine x plus y, I should say. Okay? So all the stuff with dy dx's goes onto one side, and all the stuff without the dy dx's goes to the other. So I'm going to subtract over the 2y cosine x dy dx. And then subtract over the cosine xy. Sorry, x plus y. Everybody okay there? And now we can, oh my God, come on now. Stop. Can I just like, thank you. Ugh. All right, so I'm going to factor out the dy dx. and then divide that bracketed expression to both sides. And I'm going to call that finished at that point. I don't think there's any obvious cleanup to do from there. This is probably about as good as it's going to get. Is everybody okay with the cleanup algebra at the end to just isolate the dy dx?
So in that case, we do have to do some algebra to do idea by itself.
Right, because it's asking what does y prime equal. So the direction there tells you I need to get a y prime by itself, or a dy dx. Those two things get interchangeable, right? I just choose to do the dy dx because it's easy to lose the prime symbol when I'm copying stuff down. And then it's like, oh no, where's my y prime at? I did something and combined it with something else, and oh no, it's gone, and like I made a big mistake. I just do the dy dx because it's copying that. It's I'm less likely to screw that up. But you can do primes, it's fine. The next one here is asking for the second derivative. Ooh, scary. Well, we start the same way. So we got to get a first derivative out of this. Oops. Oh, yeah. Okay, the derivative of x to the fourth is? 4x cubed, right? And then the derivative of y to the fourth is?
4y cubed dy dx.
Perfect. And the derivative of 16 is? Great. So pretty easy. We just subtract the 4x cubed from both sides and divide by 4y cubed, and we're done. So I did the reducing there in my head. Is that okay with everybody? Okay. So I'm going to put a little box around that, or highlight around that, because I'm going to need that later. But I don't want dy dx, right? It wants the second derivative. So I'm going to take this and now do the derivative of both sides again. Is everybody okay with what I did there? So the derivative of y prime is just y double prime, right? So the derivative of this, the way we write that, the way we write the second derivative, is d squared y dx squared. Because it's like having two of these things and then a y. Is that okay? So that's just like the notation for a second derivative. To do the derivative of this, what am I going to need to do? Quotient rule, great. So bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. So far, so good. Okay. The derivative of y, or of negative x cubed is negative 3x squared. And then I have minus and negative, so I'm just going to write a plus. And the derivative of y cubed is 3y squared dy dx over y to the sixth. Now, remember how I put a little highlight around this thing? gotta go drop that answer back in, make a substitution to get rid of the dy dx in my second derivative. Is everybody okay with that? My advice to you is usually you want to do that as soon as you see it, but you know, there may be some like specific algebraic reason why you may not want to do that. But is everybody okay?
If it's in the parentheses with 3y squared,
So if there's a free response question, you could be finished at this point. If it's multiple choice, this will not be what any of the answers looks like. You'll need to do some reducing. So I would start there, right? I think is what Lucia you're going to ask to be able to do. Absolutely can do that. I still have a y denominator though in that second term in the numerator. Everybody see that? So I would do this to kind of get rid of that. So I'm going to have negative 3x squared y to the fourth plus 3x to the, I should say it's minus now, to the sixth. No y's over y to the 7. And that's probably as good as we can do. Does that feel okay? Algebra was yucky, but like manageable once we've got it, right? The calculus piece wasn't difficult other than you got to remember those dy dx's, right? Okay. So what we want to do next, we're going to introduce some new derivative shortcuts or derivative rules for the inverse trig functions. So I'm going to go ahead and prove this first one to give you a feel for how that works. Everybody's okay? So recall y equals sine x and y equals sine inverse x are inverses. Everybody's cool with that statement? Do you remember if we go back and we look at the inverse section, we said if two things are inverses, then the derivative of g of x is equal to 1 over f prime of g of x. I'm going to take advantage of that. Where were we? Here. So if this is like my f and this is like my g, I can say that sine inverse of x is equal to 1 over cosine of sine inverse x. Is everybody okay with what I did there? Does this look like a problem you would have done in pre-calculus? Cosine of sine inverse x. Right? Do you remember how we do that? So we take the inside and say, okay, well, sine inverse of x is equal to some angle. And that's the same thing as saying sine theta is equal to x. And we remember that sine is opposite over hypotenuse. So we think about a right triangle. Let's go down here. Where the opposite side is x and the hypotenuse is 1. Does this ring a bell? what I'm doing or no? Lucy is upset that we're doing this, it looks like, but I can then use the Pythagorean theorem to solve for that third side of my triangle. So I'll just call it y for the sake of argument. So x squared plus y squared is equal to 1 squared. So y squared is equal to 1 minus x squared. So y is plus or minus, I guess I should say, square root 1 minus x squared. But because we are talking about the side length of a right triangle, I can drop the minus from the plus or minus, right? Everybody's okay there? So cosine of theta is adjacent over hypotenuse. And that's what we're trying to end up with. Would I ask you to repeat this on a quiz or a test? No. I will say, though, in the future, in second semester, there's a technique called trigonometric substitution that'll involve, like, making a right triangle like this to make a substitution, to make a problem doable for us. I will warn you now that this type of problem is not going to go away, that it'll come back in second semester, even though I would not ask you in first semester to do this kind of proof. And we'll do much more example in second semester when it's time to do this. But I want to just warn you that, like, this idea of, like, building a right triangle with the side lengths variables and then doing a substitution is not going to go away. That's going to come back. So just put that in the back of your head and be like, oh yeah, Mr. Cook warned me this was going to come back. I'd forgotten that, but now that he says, like, remember when I said in first semester that blah, blah, blah. You're going to go, yeah, he did say that. We're going to skip the proof for tangent inverse. We'll just state it. It's the same idea. You do it the exact same way. This is the collection of all the derivative shortcuts for the inverse trigonometric functions. Oh joy, more things to memorize. Add those to your list. These are the worst ones because they all look like the same to me, right? It's like, oh, Mr. Gulick, are you joking? Unfortunately, I am not. So yeah.
Did you say that we would get you would give us like something that has all these on them?
Yes, I have a Quizlet. Once we finished all the derivative shortcuts, I will publish that into the My Notre Dame that you can use to review on.
Okay.
Noah.
What's the difference between cosecant and the secant one?
A negative sign. The cosecant has a negative.
Oh, I see that.
What I would say that the way I remember this, so just like for the regular trig functions, all of the ones with a co-prefix are the ones with a negative sign. So just like the derivative of cosine, cosecant, and cotangent are all negative, the derivative of cosecant, cosine, and cotangent inverse are all negatives also. That's helpful to remember, right? Otherwise, you're kind of, up a creek other than like, they're basically the same thing with opposite signs, cosine and sine. Cosine and cosecant, basically the same thing with opposite sign. If you can remember one of them and then cosine, or the co-functions all get the negatives, it's not so bad. That, I guess, let's do these examples here. And then we'll move on to start the next section. So here we want the derivative of y equals 1 over sine inverse x. To differentiate this, what do we need to use? Quotient rule is the natural first thought, right? I would encourage you not to use the quotient rule on this. I would think about this as a chain rule.
So it's like 1 over x.
Yeah, I would think about it that way. Now, could you use a quotient rule? Absolutely. Will you get the same answer? Absolutely. Will it be like a little messier? Yeah, I think so. Because this guy, I can do in my head. So, the derivative of the outside is going to be -1 stuff to the -2, right? Times the derivative of the inside which is just my shortcut. And I'm done. Is everybody okay with what I did there? Again, you could do a quotient rule. Not wrong to do that. I think that's easier. I think that's cleaner. I think that's less stuff rattling around. There's no combining of like terms in a numerator to handle. It's done. I like that better, personally. But the quotient rule would not be wrong to do there. In fact, every quotient rule problem you could do as a product and chain rule, where like numerator times denominator to the -1. You could do it that way if you prefer. You get the same answer. Sometimes it's beneficial to do it that way. Not often, but sometimes it could be. Or if you just forgot which one was negative in the quotient rule, it's like, oh no, I'm doubting it. Just write it as a product of it with a chain rule, and you automatically get the negative sign right. Assuming you can do the calculus, but you don't have to memorize it that way. I did that a lot when I first encountered this. It was just like, I'm gonna do these as chains and products because I could never remember, like, I'd always doubt which one was supposed to be the -1. Like, is it, derivative of the top times the bottom minus the derivative of the bottom times the top, or is it reversed? And I'd sit there and like, oh my gosh, I can't remember. Product of, product in a chain rule I don't have to remember. Just did it that way for a long time. For B, x times arctan of x. Remember, arctan and tan inverse mean the same thing for all intents and purposes. What do you notice there? To differentiate that, what are we going to need to use? Product rule and a chain rule. Right? See the square root of x inside the arctan? Which one do I start with? Product rule is correct. Yeah, get it. So we have x times the derivative of, I'm just going to write as tan inverse. And I'm going to write x as square root of x is x to the 1/2. Everybody so far so good? Okay. So this guy is my chain, right? The derivative of the outside is going to be 1 over 1 plus stuff squared times the derivative of that stuff . Is everybody okay with how I applied the chain rule there? Take a look. If you want me to pause so you can process, let me know. Otherwise, I'm going to keep bulldozing ahead. But if you need a minute to look at it, be like, oh, okay. Take a minute. All right, nobody's saying anything. Here we go. And just keep copying the rest. The derivative of x is just 1. You don't need to write it. I'm going to write it since they're notes. And then we have one more derivative to take. I'm going to simplify x 1/2 squared is just x. And then this is done as far as a free response question goes. If I wanted to continue simplifying, I could write it as, what do I say, square root x over 2 times 1 plus x plus tan inverse square root x. I think is how that would end up being written. You see the combining that I did there? That'll wrap up section 3.5. So the first half was like these implicit differentiation problems. The second half is going to be these trig inverse derivative problems. That's like 3.5, it's just differentiation. Just adding some rules and a little bit of a new technique where we have these implicitly defined functions. On to 3.6, here where you're going to be introduced to your last derivative shortcuts or derivative rules for the entire course. They are how to do the derivatives of logarithms. So our first rule says the derivative of log base a of x is equal to 1 over x times the natural log of a. I'm going to prove this much in the same way I did for sine inverse. I'm going to use inverses. So a to the x and y equals log base a of x are inverses. So I know then that the derivative, and this is like my f and this is like my g, I'm going to use that same inverse formula from before, is equal to 1 over the derivative of f, so a to the stuff times the natural log of a. What is a to the log base a of x? Composition of inverses, right? So it should equal what? You're close. Did you say 1?
Yeah.
You're close. X. X is what it's going to equal. Like exponent base a cancels log base a, and you're left with just x. Maybe she can and aren't done more done. Notice that we didn't prove that the derivative of a to the x is equal to a to the x over times 1 over a, or I'm sorry, times the natural log of a. That's actually much harder. If you have 1/2 of the inverse, the other half of the inverse is really easy to prove. The first half is rough. Either, depending, whichever one you want to start with. Once you have 1, the other is easy because you have a formula and the chain rule. The first half, getting the first half is rough. That's why we can do it. Why is this one going to work? I can do this with just this statement. Yeah, so if I just let A equal E, then it's the previous formula, right? Because in the denominator I'll have x times the natural log of E, and what's the natural log of E?
That's 1.
1. Everybody's okay? I know, logs. All right, let's practice using this. So here we want to differentiate y equals the natural log of x cubed plus 1. When you look at this, what do you see? What derivative rules are we going to need? Chain rule is correct. Good. The derivative of the outside is 1 over x. So 1 over stuff. And then times the derivative of the insides. Everybody's good?
You said that y prime is the same as d over dx.
dy dx.
dy dx.
dy dx. And so when I do the derivative, I get 3x squared. So it simplifies down just to that, right? What are these two formulas saying? It's just this rule plus the chain rule. That's all it is. It's just that rule, the chain rule built into it. Do you need to memorize those? No, because you have the chain rule memorized. You have the other rule memorized. You can use the two in conjunction like we just did there. Do I need to memorize those?
No.
No. It's just a like, oh, look at this. You know, like we could have done this for every one of the derivative shortcuts and like wrote another version with the chain rule built into it. But like, chill, guy. All right. The nice part about this is that these are often, because of the nature of the natural log, where you're getting like 1 over stuff, problems where reducing happens pretty nicely. These make good multiple choice questions because they really test you on your reducing. So if I want to do the derivative of the natural log of sine x, notice the chain rule. I could just do this. What's the g of x in this case?
Sine of x.
Sine x. So I'm going to have derivative of sine x over sine x.
Cosine over sine.
Make sure we're writing the variables. Cosine x over sine x. Again, when I looked at some of the recent stuff, you guys are kind of getting a little, some of us are a little sloppy about dropping variables in our tricks things. Be careful on that. Again, on a quiz or whatever, no big deal. On a test, I have to make deductions. Cosine over sine. Not tangent. Cotangent. Yeah. And if it was a multiple choice question, that would be what the final answer would look like.
Sine over cosine is tangent?
Sine over cosine is tangent, yes. And I think I have the basic trig identities sheet in here for if you want to, you're like, I need to bone up on this a little bit. I would say nothing past here is necessary. Yeah. Mm-hmm. Okay. Let's look at the next one. What do you see?
Chain.
Chain rule. Notice where's the chain though? It's at the start, right? The outer function is chained, right? The outer function is around the natural log. Can I use this? No, because the square root is around the natural log, not the natural log around the function, right? It's wrapped in the reverse packaging. So I would just think about this way. So the derivative of the outside is 1/2 stuff to the negative 1/2, and then times the derivative of the inside. Does everybody see it? So this is just like a power rule. So the exponent becomes the coefficient. I subtract 1. Is that good? You guys feel okay? All right. I'm just going to bulldoze past this because I want to do this one. And this will be the last example we'll do today. We'll stop it after this one because I feel like you guys have had enough. So if you look at this guy, what do you see going on?
Chain, product, or quotient.
And then another chain rule for the square root x plus 2. So there's 2 chains and a quotient, right? You see it?
ln is a chain.
Yep.
Okay.
You see it?
Yeah.
Okay. I wouldn't do it this way. I would do this as, I can do this with 2 chains only, no quotient necessary. Mr. Coolidge, you have my attention now, because I love avoiding quotient rules when I can, because boy, that's a pencil eater. How are you going to do this? Who remembers their properties of logarithms? So we have product, quotient, and power properties of logarithms. If you don't have those memorized, add them to your list. They come in so much handy. Now, you remember doing this in pre-calculus and honors algebra too? Should, because we did them in both of those places. So ideally, this is something you already have like mostly memorized, and it's like, okay, I just need to like refresh a little on that. Because at one point I did have it, and it just kind of like, you know, over the summer faded a little bit. So it won't be a huge pull to bring that back, but you will want that. So for this particular problem, we start by expanding this logarithm. What's the order that I apply my properties of logarithms when expanding? Quotient, product, power is my order for expanding. That's the direction that you will likely be wanting to go in doing these. So quotient, product, power. Is there a quotient property going on here?
Yes.
Yes. How would I rewrite this? And instead of writing as a square root, I'm going to write it as a 1/2 power. And take advantage of, well, there's no product properties going on, right? I don't have anything multiply going on. But I do have an exponent. Let's do the power property there. So I can do that. Everybody okay there? Now, given the choice, would I rather differentiate this or this? Give me the second one every single day of the week. Boy, that's so much simpler, right? That's just going to be, yeah, this chain and quotient, or sorry, chain and log rule together. So derivative of the inside over the inside. Derivative of x plus 1 is? 1. Over the inside x plus 1. X minus 1 is the, or x minus 2 is the inside. Derivative of the inside is? 1. Over the inside. Done. Now you can make some common denominators and combine that into one thing if you needed to. We could do that if we would like. What's that going to look like? It's going to be 2x minus 4 minus x plus 1 over 2 times x plus 1 times x minus 2, or x minus 5 over 2 times x plus 1 times x minus 2. Right? Just making some common denominators and combining that terms there. But this is fine for like a free response. That's probably the way it would be written as a multiple choice question. They might even foil it out if they're really rude. Ugh. This is where I'm stopping. Okay? The homework quiz for tomorrow is going to cover only implicit differentiation. No inverse trig derivatives will occur because I'm not going to ask you to memorize those in a day. Right? Like that's I think an unfair ask. Or unnecessary anyways. We don't need to memorize them in a day. You can take your time. Okay? So it'll just be implicit differentiation. It won't have any inverse trigs.
Is it 2 questions?
Yeah, 2 or 3, I don't remember. Something like that. So, okay. And we'll finish, next time we'll finish 3.6, and we're going to finish 3.7. 3.7 is just like, we have all the tools that we need to do it. It's just like, here's some story problems that involve differentiation. So we'll just kind of do some examples and it'll be done. I'm up.
Would you say the test would be Friday next week?
I mean, it's possible, that would be the earliest possible date it could occur.
Okay.
So we'll see how things, you know, we still have to do 3.6, finish 3.6 and 3.7. Still have to do 3.10. We need to take at least a day for a review. I'll kind of see where things are stacking out. But that would be the earliest possible date.
Okay.
Matthew.
Would 3.7 also be due Sunday then?
Yes, but I think there's like 5 questions or something. 3.7.
And then like for
Sure.
Well, they might have a lot of parts. But it's like mostly algebra.
I'll just start
On
tonight.
Sundays,
That's what it looks like, yes.
No.
Do we need to memorize the derivatives and inverse trig functions for the next quiz?
No.
Okay.
I think that we could just wait
Okay.
on memorizing those. I will, though, try to find that Quizlet and add that Quizlet into the minor name right now.
Okay.
Let me try to find that for you guys. Okay.